this section, we'll be taking a look at some applications of linear functions as they apply to business. There are three things that we're going to be looking at, and that would be the revenue, the amount that's taken in by selling an item, the cost to produce the item, and the profit, which is the difference between the revenue and the cost. Let's get started. In our first example, an anti-clot drug can be made for $10 per unit. The total cost to produce 100 units is $1,500. So let's write that down. $10 per unit and $1,500 for 100 units. Well, if you multiply 100 by 10, you're going to get 1,000, not 1,500. So where does that extra 500 come from? The extra 500 is what we call the fixed cost of producing the drug. Okay, there's obviously some kinds of equipment we have to produce this drug, also some kind of facility, and those are fixed costs. We have to buy that equipment and house it in a facility, whether we make many units or just a few. So let's look at finding a cost function. So for a cost function, we call that usually C of x. We've got $10 per unit, so $10 for every unit plus some fixed cost. And like I said, we have 500 more here than is accounted for by the $10 per unit. So we're just going to say plus 500. And this is our function. And the fixed cost then would be $500. Pause the video now and work on checkpoint 1. In our last example, we looked at the fixed cost and the per unit cost for producing a drug. And now we're going to look at a new idea, the average cost. Because we've got that fixed cost, part of that fixed cost has to be paid for every unit that is produced. If I produce a lot of units, then I have more units between which I can divide that fixed cost, and so the price per unit actually goes down. So let's look at a new idea, C prime, which is the average cost, or C bar, is C divided by X, C of X divided by X. So from our last example, C of X was 10X plus 500. And then to get C bar of X, I just divide by X. And so this gives me now 10 plus 500 over X. That's my C bar rule. And now I want to know, what is C bar of 100? So I replace this X with a 100. 500 divided by 100 gives me 5. So this is 15. So if I only make 100 units, each unit is going to cost me $15 to make. What happens though if I make 1,000 units? Then I've got 10 plus 500 divided by 1,000. So that's going to be, this is going to be 0.5 So 10.5 or $10.50 if I make 1,000. So this is what we call economy of scale. When I make more units, I can produce each unit more cheaply because I've divided up those fixed costs. Pause the video now and work on checkpoint 2. Before we work another problem, I'd like to just recall to your memory the idea of rate of change. And in a linear function, the rate of change is equal to the number that's right next to the x, the m, or we call it the slope for a linear function. So, in this example, according to Kelley Blue Book, a Honda Civic 4-door sedan that is worth $24,535 today will be worth $17,020 in 3 years if it is in excellent condition with low mileage. We're going to assume linear depreciation and find the depreciation function for this car. So we start with that linear function, y equals mx plus b. I like to think of b as where we begin. So where did we begin? At $24,535. Now we just have to figure out m. Now I'm going to change this over to, well, not c of x. What am I going to call this? We'll just leave this as y. And you might recall, to find the slope, we can take these 2 points that we have. So I'll take 24,535 minus 17,020. That's the change in value over the change in time, which is 3 years. So this was 0. This was time 0, and this was 3 years later. Okay, and I get for this then negative 2,505. So we can say that this is the rate of change. We're losing $2,505 per year in the value of the car. So now I can say y equals negative 2505 x plus 24,535. Okay, now that we have this function, we want to know what will the car be worth 5 years from now. So all we need to do is put in a 5 here. I've got y equals negative 2505 times 5 plus 24,535, which tells me that in 5 years my car will be worth $12,010. And then they ask, at what rate is the car depreciating? And this is what we figured out when we found M. The car is losing value, $2,505 per year. And now we know that cars don't depreciate linearly. They lose much more value when they're new than when they're old. But this is just an example that's been simplified a little bit for us. Pause your video now and work on checkpoint 3. Another number that we like to know in business is the marginal cost. The marginal cost can be described as the cost to produce one more item. We've seen that the cost overall per item goes down as we produce more and more. But now we want to find out what's the cost to just produce one more. So we're going to start with this. We have a cost function for producing a electronic tablet, 160x plus $750,000. And we're first asked, what are the fixed costs for this product? Well, fixed cost is what we start with. That's what we need to set up. So our fixed cost is the $750,000. Okay, now we want to know the marginal cost. The marginal cost, very simply, is the slope. That's how much it costs to produce each item, $160. But now the next question is, after 50,000 units have been produced, what's the cost of producing one more? So this is a little more complex. We know that it's going to cost us $160 to produce that, but we also want to know what part of this fixed cost should be applied to that next unit after 50,000. So what we're going to do is find C of 50,000, which is equal to 160 times 50,000 plus 750,000. And this gives us a total of 8,750,000. This gives us a total cost of 8,750,000. Now, what would it cost us to make 50,001 tablets? I set it up the same way. And now I get a total of 8,750,160. So the difference between these two then would be $160. So we call this the marginal cost. Does that mean that we're not paying any of the fixed cost on this? It doesn't. But what the part that we've paid, the fixed cost at this level, is so small that it rounds off. If we're going to round to the nearest dollar, it would be less than half a dollar. So that's why the marginal cost at this level is the same as the variable cost that we had at the beginning. Pause your video now and work on checkpoint 4. Along with marginal cost, we also have marginal revenue, which is what's the change in revenue from producing one more unit. Let's take a look at an example. The energy company, New York State Electric and Gas, charges each residential customer a basic fee for electricity. So we've got a basic fee, $15.11. And then they charge $0.0333 per kilowatt hour. So this is the charge for the amount of electricity that you use. Okay, assuming that there are 700,000 residential customers, find the company's revenue function. So the revenue from the basic fee is going to be 700,000 times $15.11, which gives us $10,577,000. Okay, that's just for the basic fees. If X is the total number of kilowatt hours used by all the customers, then we have 0.0333 times X. So we could write an equation. The revenue is equal to 10,577,000 plus 0.333x, where X is the number of kilowatt hours consumed. Okay, what's the marginal revenue? The marginal revenue, again, is the rate at which this function is changing. Put the decimal point in the right place. And so this is the marginal revenue. Every kilowatt hour basically is going to give the company 3 1/3 more cents. Okay, so just to recap over the last two examples, the marginal cost is the cost that it takes to produce one more unit. And the marginal revenue is the change in the revenue by selling one more unit. Pause your video now and work on checkpoint 5. As I said at the beginning of this video, another thing that we're interested in is the profit. And that profit can be found by taking the revenue and subtracting the cost. So we'll look at an example of that now. A company manufactures a 65-inch smart TV that sells to retailers for $550. The cost of making X of these TVs for a month is given by the cost function. So we're going to say $550 is the price to retailers. And then they give us a cost function of 250 x plus 213,000. So there's my cost function. It says find the function R that gives the revenue from selling X TVs. Well, the revenue, very simply, is going to be 550 times X What is the revenue from selling 600 TVs? R of 600 is equal to 550 times 600, which gives us $330,000. What's the profit function? Well, remember, profit is revenue minus cost. So we'll just put in here 550x minus 250x plus 213,000. Well, we know that 550x minus 250x will give us 300x minus the 213,000. So that's our profit function. Now they want to know, what's the profit from selling 500 TVs? We'll bring our profit function up here. The profit for 500 televisions is 300x minus 213,000, and I'm going to replace that x with 500. So this is going to be 150,000 minus 213,000, which gives us actually a negative number, negative 63,000. So this is telling us that if I only make 500 TVs, I'm not going to make a profit. So I either have to make more televisions, or I have to raise the price to retailers, or find some way to make them for less. So if I can't make a profit by manufacturing and selling 500 TVs, how many TVs do I have to make a profit? Finding this number is what we call the break-even point. So we're not looking really to find a profit, but when is the revenue going to equal the cost? So I will break even. Anything after that could be considered profit. So we're going to look at this last example that we did with the televisions. And we want the revenue to equal the cost. At that point, we'll break even. So our revenue was 550x, and our cost was 250x plus $213,000. So I'm going to subtract the 250x and that gives me 300x equals the $213,000. And then divide both sides by 300. And I find that to make a profit, I need to manufacture and sell at least 710 television sets. Pause the video now and work on checkpoint 6. In the first part of this section, we looked at cost and revenue and how they're related and how they are also related to profit. In the remaining examples, we're going to be looking at supply and demand. These are two other economic quantities that are related to one another. In our first example, we'll look at this situation. Suppose that an economist has studied the supply and demand for aluminum siding and has determined that the price per unit, P, which a unit might be, say, 1,000 square feet of siding, and the quantity demanded, Q, are related by the linear equation P equals 60 minus 3/4 Q. Okay, and just a reminder, P is price, and Q is quantity. Okay, and the first part of our question asks us to find the demand at a price of $40 per unit. So we're going to put 40 in the place of the P, 60 minus 3/4 Q, and then just solve this. We get negative 20 equals negative 3/4 Q, and when I multiply both sides by 4/3, let's make it negative 4/3 so we get rid of all of our negatives. This is now going to be 80/3 is equal to Q. So if the price is $40, the quantity demanded would be 80/3, which is approximately 27. Okay, just a little under 27. The next part of this problem asks us to find the price if the demand is 32 units. So we're going to use this same equation, but this time instead of substituting for price, we'll substitute for Q, quantity. So I'm going to have P is equal to 60 minus 3/4 of 32. Well, 1/4 32 is 8, so 3/4 would be 24, and 60 minus 24 would give us 36. So the price for the quantity of 32 would be $36. And we are asked now to graph P equals 60 minus 3/4 Q. So to graph that, I'll put quantity on the horizontal axis. We'll make this Q. And we'll put price up here on the vertical axis. And we're going to make each axis go out in increments of 10. Oh, forgot 70. Okay, and we have 2 points that we got from working the equation with 2 different values. Okay, the first point was we had a P of 40. So that would be here, and when P was 40, Q was not quite 27. So we're going to put a dot right there. And in the second part of the problem, we had a demand, a Q of 32. So about here, and at that point the price was 36. So just about there. So our 2 points are pretty close together, but even so, we can use them to form a line. And graph our function. And this shows us, if I had graphed this perfectly, I have an intercept here at Q equals 80, and another intercept here at P equals 60. So that's graphing a supply and demand graph. Now that we have this graph, we can use it to find other combinations of P and Q. For instance, suppose we were asked if the price was $30, what quantity would be demanded? To find out, we'll go to 30 on the p-axis and come out here and see that the amount demanded would be 40, so this would be the point 40, 30. We use the x-coordinate first. The next question says, at what price would 60 units be demanded? So now we're going to go out on the q-axis, and we see at 60 it looks like about 15. So this is another point, 60, 15. Okay, and then finally, what would be the amount demanded at $60? Well, if I come all the way up to $60, I see that I'm right back on the y-axis. So basically, if it's $60 per unit, nobody's going to buy any. There won't be any demand. Pause your video now and work on checkpoint 7. In this example, we're going to continue on with the same situation we did in the last one. Suppose the economist in example 8 concludes that the supply Q of siding is related to its price by the equation P equals 0.85 Q. So let's write that down. Find the supply if the price is $51 per unit. So again, we can just put in 51 here equals 0.85 Q, and then divide by the 0.85. And we find that Q is equal to 60. So if the price is $51 per unit, the quantity demanded would be 60 units. Now, if the supply was only 20 units, what would the price be? Now we're going to look at P is equal to 0.85. This time we only have 20 units available. Okay, when there's not so many units available, what would we expect for the price? That it would go up. Okay, so 0.85 times 20 gives me 17. So if the supply is 20, the price is only 17. We're going to graph this now on the same graph that we had for the previous example. Okay, and this is going to start at, in this equation, if P is 0, Q is also 0. So we're going to start at 0, 0. And real easy, if Q is 10, then P would be 8.5. And just to get another point that's maybe a little easier to work with, we had a point 60 and 51. So Q is 60, P is 51. So there's that curve. And now we're asked to find the approximate price at which 35 units will be supplied. So we'll come out here to 35 units and find a price there on this graph. Looks like it's going to be just under 30, so we're going to say price is approximately, let's say $27. Okay, now we're going to use algebra to find the exact price. So if I have 27, well, I'm not going to use 27, that's my approximation. P is equal to 0.85, and they're telling me 35 units are supplied, which gives us 29.75. So my estimate was a little bit low, but reasonably close. And when the supply of a quantity exceeds the demand, we say there is a surplus of supply. When demand exceeds supply, there is a shortage of supply. So I've left the curves up here. This was from example 8. This was from example 9. And it says, determine graphically whether there is a surplus or shortage of supply at a price of $40 per unit. So $40 per unit is here. And we're asked to find which one is more. Okay, this graph is the supply. And this green graph is the demand. So at this level of $40, the supply is larger. So we could say at P equals $40, there is a surplus of supply. When the supply curve and the demand curve intersect, we say that the system is in equilibrium. And we could try to find that point from the graph, but it's more accurate to use algebra to find the point. And this is how that's done. My demand equation was 60 minus 0.75 Q. And my supply equation was 0.85 Q. So when these two things are equal, I'm at equilibrium. So I'm going to add 0.75 Q to both sides. I have 60 is equal to 1.6 Q. And then when I divide by 1.6, I get that Q is equal to 37.5. So my quantity is 37.5 units. To find P, remember that P is equal to this equation here, 60 minus 0.75 Q, and we've determined that Q is 37.5, so this is 0.75 times 37.5. And it gives us a value for P of 31.875. So if we rounded that off to dollars and cents, it would be $31.88 for our equilibrium price. And then our equilibrium quantity would be 37.5. Okay, pause the video and work on the last checkpoint before you go on to your assignment.